Yes, the last one.
Okay, so what I want to do is complete the proof. What I want to do today is to complete the proof and of the theorem. So yesterday we reduced the problem to study the eigenvalues of the 4x4 matrix, which has, thanks to the simplicity and regressivity property that we preserved during the proof, it has the form of G4 times a matrix B unit epsilon. The matrix B unit epsilon is a 4x4, and it has 2 times 2 block, in which the diagonal block are self-adjoint, and instead it's a outer diagonal block F. And remember that this matrix is the matrix representing the action of the operator L mu epsilon equal J B mu epsilon on the 4x4 space spanning the perturbed eigenvalues, and the operator B mu epsilon it is here and we put it explicitly. Okay, so what I claimed yesterday is that this matrix 4x4, which we wrote down, has the following asymptotic expansion when mu and epsilon are small. And now what I want to do is first to comment about this expansion. And in particular, what I hope I have convinced you yesterday is that if you look at this block, so you see that this block, when you multiply this matrix, so we need to make J4 times epsilon, and so this is also given by J to E, J to F, J to F star, J to G. So this matrix J to E, it has 2 unstable eigenvalues provided this element and this element have opposite sign, which the moment you see makes sense, so because here there is epsilon square minus u square over 8 plus correction, lower order correction, and here there is minus u square over 8. So they have different signs, so this is this will give the Benjamin difference stability. Okay, so now I want to comment on how to obtain this expansion, and I want also to notice that this is not Taylor expansion. It's not just only Taylor expansion. And it's not a Taylor expansion because this term in this entry, in the entry 2, so in this entry, there are no terms of order epsilon to the k for any k. There are not, and there are no terms of order mu epsilon to the k for any k. So this starts with minus mu square over 8 times 1 plus some corrections. So these are infinitely many terms that you need someone to cancel out or to understand that they are not here. Okay. These terms will be very dangerous if you don't control them. I mean, if you try to compute them, let's say you try to compute the terms for the epsilon square here, you discover that it's 0. Because there is no. But you cannot, and so in principle, you can then there is a correction of order of epsilon to the free. But this would be dramatic, no? Because it would destroy the sign of this term. So in order to have a Benjamin Ferenc stability, you need this and this to have opposite sign. And if in this element you have something like O of epsilon to the 100 minus mu square over 8, well, you know that this is positive, you need to control the coefficients. To know that this is negative, you would need to control the coefficients. And so you cannot just ignore this term. And so the only possibility is to prove that indeed there are no terms of this type for any. Okay, and now I want to explain why. Okay, I will explain this. No. Okay. So let me. I want to now what to do. So first, I will explain. So how to compute the generic good term, this expansion, for example, this, and then why there are no terms of this type for any k, and then we do the block diagonalization. So we'll be quite quick on the first part because I always say that I will be quite quick and then I will slow. Okay, so let me include the expansion. Proof of the expansion. Okay, so it's going to be there are essentially three terms. So the general term is the term in which you can do a Taylor expansion. So general term, you make a Taylor expansion. So for example, this one can be treated with a Taylor expansion. And what do you do? So how do you do this? So you do this because everything is explicit at the very end. So remember that F1 plus mu epsilon is mu sin u epsilon transformation operator applied to F1 plus. But then this operator is explicit and it is identity minus p mu epsilon minus p00 squared to the minus 1/2 applied to p mu epsilon p00 plus identity minus p mu epsilon identity minus p00 applied to F1 plus. And all these objects, so the spectral project, so the projectors depend analytically on the parameters, so you can expand them. So you Taylor expand them. In this case, and when you Taylor expand, you get you Taylor expand this binomial series, so you get p mu epsilon f1 plus 2 p mu epsilon minus p00 square p mu epsilon f1 plus a little correction, then you keep expanding the projectors, and so you get the projector of the first order is the aperture eigenvectors f1 plus, and then there is a correction, so we say epsilon derivative with respect to epsilon of p mu epsilon evaluated at the 0 at the plus 1 and so on. No, this you can compute. And these objects, so the projector you can compute here explicit formulas. So for example, the derivative, derivative respect to epsilon of p mu epsilon evaluated at 0, what is this? So you need to take the derivative of the solvent essentially. So you get formula like this, and then when you evaluate at 0, so you get L00 minus 1 minus 1, the derivative with respect to epsilon of L mu epsilon evaluated at 0, and then L00 minus lambda minus 1 in the lambda, and to this operator but then you can compute the action of, for example, for this jet, you can compute the epsilon p mu epsilon evaluated at 0 of f plus 1 using a little bit of complex analysis. Okay. And so, for example, for this term, let me just give you so this is the integral of the gamma L00. So let me move here. So F1 plus, when I apply to F1 plus, I apply here F1 plus lambda. And so what do you get? So you see, so remember F1 plus is the unperturbed eigenvectors. It is in the kernel. So what is this? This you can compute explicitly. Because you know everything, you know the operator, you know this expression, that you can compute this and eigenvector will give you minus 1 over lambda F1 plus. Because is an element of the kernel. Then this object you can compute it. You can compute it because you have the expression of G epsilon. You have J, you compute this object at 0, and for example, you discover that you discover that when you apply this to this vector, which is also explicit, you find something like twice sinus of 2x 0, 1 over lambda. Okay, and then you have another solvent for applying. But again, this is explicit. This operator is explicit. As soon as the first computation is applied to this vector, you find something like 1 over lambda, and then minus 2 cosinus of x minus sinus of 2x plus lambda times function which is analytic lambda. And okay, and then you need to integrate over a circuit. So remember that gamma is a circuit in the complex plane isolating zero. And so you have a integrating function, receiving theorem. This you know, but you don't need to control because it's an analytic function. Cancel out, and the other contribution by this. And so this way you can control how the jet of the projector and of the translucent operator acts on the N1 plus. And then, for example, you want to compute this element, so what is this element? So remember that entry, we quantify it precisely, and this was so this entry E11, that we put this entry, let me do this E11, and so E11 is given by the scalar product. E11 is given by the scalar product between B mu epsilon, the operator, with F1 plus mu epsilon, F1 plus mu epsilon, F1 plus mu epsilon. Okay, but now we have the theory expansion of everything. Take the theory expansion, plug it in, close yourself in your dark office at night so no one disturbs you, and compute the theory expansion. Or otherwise, take Mathematica and let Mathematica do the computation. And now, thanks to Javier, we know that we can trust Mathematica symbolic of Mathematica. And okay, but we also use Mathematica at some point. So when you need to compute your expansion, so you plug it in. So when it's a this you plug in, you have Mathematica compute the object. And so, for example, here you will discover that there is epsilon square minus mu square over 8, blah blah blah, plus something else. And for example, there is no term for the epsilon times mu. This will cancel out with the computation discovered. All right. So this will solve many of these elements except for this one. Now I want to convince you. So this needs a different analysis. So we determine E2, and for this, so we need to be sure that there are no terms for the epsilon to the k for any k. There are no terms for the mu epsilon to the k for any k, because this would destroy the vector differential structure. If you do not control this fact, if we do not control that there are no terms of this type, we would not be able to work the J2E as two eigenvalues with positive real number. Okay, so and here, okay, so let me start with this one. So about the about O epsilon to the k. Okay, so okay, so let us consider the matrix B0 epsilon. So because terms of this type comes when mu is equal to 0, so this term. So consider this matrix B mu epsilon. What is this matrix? So this matrix is done by taking the scalar product of B 0 epsilon F1 plus 0 epsilon with F1 plus 0 epsilon, blah blah blah, and then all the other terms, and so on. Okay, what do we know? So let me write them perhaps also the second term. Let me write the second term. Let me write the second term here. So B of 0 epsilon, F1 minus, and then we have B 0 epsilon, F1 plus, F1 minus. So what do we know about these terms? So remember that because of the reversibility, we know already something. So we know that whatever this term are, so this must be real, and this must be pure imaginary. Okay, because this was a consequence of the property that we a reversible base. Right. Okay, so by preserving the structure, the base is reversible, meaning that remember, otherwise I write here. blue. So the reversibility, maybe I can put this about this. So the reversibility is that F1 plus is that rho bar F1 plus is equal to F1 plus, and rho bar F1 minus is equal to F1 minus. So, for example, how do I prove that this element? I don't remember if I did it yesterday, that this is a real. Did I do it yesterday? No. Yes? You want? Perhaps yes, no? Yes. Okay, so okay, so this must be real, this must be purely imaginary, this is purely imaginary, and so on. They are alternatively real and purely imaginary. Okay, but the operator B mu epsilon, actually the operator B 0 epsilon, calligraphic B 0 epsilon, what is this operator? So this operator is 1 plus A epsilon minus 1 plus P epsilon dx 1 plus P epsilon modulus of D. This is a real to real operator, so this sends a real vectors into real vectors. This sends a real vector into a vector. But, and so as a consequence of this, okay, this is a real operator, and then you remember that also U0 epsilon, one of the properties that I claimed yesterday, and I told you to check, is that this was a real operator. So this sends a real vector into real vector. So the reason is that the projector is an operator, and then we subtract U, you get that this is a real operator. Okay, but then what is F1 plus 0 epsilon? This is U 0 epsilon, F1 plus. So this is a real vector, this is a real operator, and so this is a real vector. And the same for minus, because also F1 minus, it was a real vector. This was just minus sinus of x cosinus of x. Okay, so look at this element. This is real, this is real, this is a real operator, this is a real number, but it's also purely imaginary. It must be 0. So this is the purely imaginary, but by this consideration, it's also real, and so it must be 0. So this means that this matrix, this 4 times 4 matrix at 0, you already know that there are plenty of 0. So all the components, which in principle are imaginary, actually are also real, and so they are 0. And so B, 0 epsilon, it is actually 4 times 4 matrix, so by doing nothing, you know that it has, it must have the form A, 0, some other alpha, 0, 0, certain number B, 0, 0, and then there is another block, alpha, so this is the symmetric, so 0, C, 0, and then you have 0, 0. Actually, here you don't know, but let me comment a bit more. Okay, so you know, in principle, here you would have some number, so alpha tilde, beta tilde, and also here you would have alpha tilde. So by nothing else, you know this, and but moreover, what do you have here? So this last column, so you can also prove that F0 epsilon, F0 of 0 epsilon is actually always the vector 0, 1, which corresponds to the Ampere-Thorne vector. And the reason is that L0 epsilon applied to 0, 1 is always 0, 1 for all epsilon. So this is always, so this vector is always, this depends, you see immediately here, no? You see immediately L0 epsilon, what is L0 epsilon is J B0 epsilon, take B0 epsilon and apply the vector 0, 1. And while doing this, you have the x acting on 1, which is 0, and you have modulus of t acting on 1, it is 0. So this is always the same. So 0, 1 is always in the kernel of the operator L0 epsilon for any epsilon. And so because of this, you can check that the transformation operator does nothing to this eigenvalue. So, and when you transform it by capo, you get the operator itself. Okay. But then what does it mean? So what is this last column? The last column, this column, what is? This column, it has element of the form B0 epsilon applied to F0 minus 0 epsilon scalar product with something. No, sorry, this is 0. Why didn't it correct? This is 0, no? This is 0. When you apply 0, 1 to this 0, 1, you get 0, 0. And so you get that this is always 0. So this is always in the kernel, meaning the transformation operator doesn't change the eigenvector. Okay, and what is this column? So this column is done by B0 epsilon applied to F0 minus 0 epsilon, scalar product with something, but this is already 0 for any epsilon. So this means that this is 0. This means that this is 0. But remember that this matrix is just the transpose of this by the structure, and so this is 0. And so you have already this. Okay. And now what we want to prove is that B is 0. Now, because this is element, this corresponds to this element together, the definition of the matrix. These are the terms for the epsilon. So we want to prove there are no terms for the epsilon. So I want to prove that this is I want to prove that this is 0. That this is identically 0 for any epsilon. Okay. So goal, show. So B, which depends on epsilon, B is equal to 0 for any epsilon.
So now you prove that this exact. So there are no terms of order epsilon depending on epsilon alone, and then you also have to prove that there are no terms depending on new epsilon.
Yes, exactly. Exactly. So these terms will come when I take one derivative respect to mu.
Yeah, okay.
Of this operator, and then I do something. Okay. What do we know? Okay. How do we prove that B is 0? So what is L0 epsilon? L0 epsilon is then here J4 B0 epsilon. This is something that you can compute easily, and this is 0 minus A, 0 minus alpha, B, 0, 0, 0, 0 minus alpha, 0 minus C, 0, 0, 0, 0. What do we know about this matrix? What is this matrix? So, what is this matrix? So this is the 4 times 4 matrix representing what? This is the 4 times 4 matrix representing the action of what? This is the matrix representing the action of what? Of L0 epsilon on the subspace B0 epsilon B0 epsilon. But what do we know about this matrix, about this operator? So we know, we studied maybe in the second class the spectrum of this matrix of L0 epsilon. And if you remember, there is the lemma by William Strauss that L0 epsilon has 0 as eigenvalue with algebraic multiplicity 4 and geometric multiplicity 2. What does it mean? for this matrix. This matrix at 0 as an eigenvalue before at 0 to the 4 is multiple to this 2. What does it mean for a 4 times 4 matrix to have this? Well, it means that L 0 psi squared 0 already psi. What is L 0 psi squared? Well, you compute L 0 psi squared. You compute L 0 psi squared, and you find that this is minus A times B, 0, minus alpha B, 0, and then you have 0, 0, 0, minus AB, 0, minus alpha B, 0, 0, 0, then 0, 0, 0. Is this, and this matrix is 0. So meaning that meaning that A times B and minus alpha times B must be 0. So there are two possibilities. So either A is equal to alpha is equal to 0, or you need B to be equal to 0. Okay, but what is A? A is this element here. What does it mean? A, for example, is A dipende epsilon, what is this scalar product of B 0 epsilon, F1 plus 0 epsilon, F1 plus 0 epsilon. And if you get pursued by Taylor, you discover that it's not 0. Discover that it is epsilon square plus other terms, and so this is not 0, so this possibility is alive, and the only one which remains is that E must be equal to 0. Okay, so you see. Okay. So you see that for example, this proof it was absolutely necessary, but the symmetries of the Hamiltonianity and of reversibility properties, because these were the one which allows us, for example, to get 0 here. So the 0 here is because we know that the matrix, the element of the matrix, must have a certain reality. And at the same time, we know that the vector must have a certain reality. This is a consequence of the reversibility property that we preserve all along the proof. And now finally we use it at full strength. Okay, so to get, so this is an algebraic property which gives us algebraic cancellation. So that is 0 for any epsilon. Okay. All right, so this solves the first problem. And now let me spend a few words about the second one. So I want to remove also the cancel. I can say here. Okay. So what about the other terms? So what about mu epsilon to the k for any k? And also here we include some algebraic problems to cancel every order, no? So to cancel just find the many terms and to cancel all of them. Okay, so well, these what are so these are the terms when you take the derivative with respect to mu of this matrix and evaluate at 0, 0. So we want to cancel all the terms of the form derivative with respect to mu of B mu epsilon evaluated at mu equal epsilon equal to 0. And in particular, there is a term, so there are various terms that you need to take care, but there is one dangerous one, and I want to explain how to deal with the dangerous term. And so, for example, here you will have a term which is
sorry, I'm there. you have to compute it at mu and epsilon equals 0.
Ah no, sorry, at mu equal to 0. You're right. At mu equal to 0, and I actually compute just this element.
Yes.
Not all of them, but this is the only element which I'm interested in. So, and the element is B, is calligraphic B, mu epsilon F1 minus mu epsilon F1 minus mu epsilon, and I need to take the derivative with respect to mu of this object and evaluate at mu equal to 0. And there are various terms, but let me write down the most dangerous one. And the most dangerous one is this, is when you take the derivative of this guy with respect to mu. So there are various terms, no? So this is derivative with respect to mu of b mu epsilon, F1 minus mu epsilon, F1 minus mu epsilon, so product, plus then you have b mu epsilon, and then the derivative with respect to mu of F1 minus mu epsilon, blah, blah, blah. And you need to evaluate all of them at epsilon at mu equal to 0. And also this at mu equal to 0. So this you can show quite easily that is actually it is 0. So there is no problem. And this instead is more complicated. What is the term? So the term is also this we can, okay. What is the term? The term is mu times, so you can compute the derivative with respect to mu of this object, and mu appears, and then evaluate at 0, and let me isolate one term of this, which is the most problematic one, which is 0, 0, 0, sine of d plus p0, which is where you take the derivative of this element. This is the problematic one, and all the rest you can show that they are 0.
What would you write? Sine of 0? Yeah.
Pi 0 is the Fourier is the projection on the 0 coefficient. Pi 0 take the function g, and it gives j0, which is the integral 0 to 1 over 2 pi, integral 0 to pi, gx. Yeah, this is the projection on the 0 put. It's the average, which comes if you make that precisely. And then you have here f minus 0 epsilon, our product f minus 0 epsilon, and then plus other terms. Other nice term. Nice in the sense that you can prove that they are 0 for an epsilon. But what about this? So what do you know about the function f1 minus 0 epsilon, f1 minus 0 epsilon? So the only thing that you know, so you know that this is a real function. You know that it's a real vector, and you know also that they are reversibility percepting. So what does it mean? Remember that rho bar takes element G1 and G2, and it gives G1 minus X and G2 conjugate, G2 minus X conjugate. And so what does it mean? What does it mean if you apply rho bar? So if G1 and G2 are real valued, what does it mean? Means G1, G2, X. So what does it mean for it? So what does it mean this? So this means that F1 minus, let me write F1 minus into components, so F11 and F12. So this means that F11 minus X, which is rho bar, and then minus F11 minus X, then it must be equal to minus F1, so minus F11X and minus f divided with s. Okay. Yes.
There is no view, right?
Here. No, sorry. Yes, but what I want to say. So let me note it. So what I want to take. Let me say it this way. Yes, you are right. So there is a mu in the sense. You are right. So this is a term for the mu something, no? Because this is the derivative with respect to mu times mu. Cioè, when I do the Taylor expansion, when I make a Taylor expansion of this element, P mu epsilon F in mu, so what do I get? So this is this evaluated at mu is equal 0, which we already dealt with F1 minus, sorry, F1 minus, F1 minus, F1 minus at 0 epsilon, plus mu, derivative with respect to mu of these coefficients. And so, and this is the coefficient. So you're right here, there is no mu, but this is a term of order. So this will multiply a mu. So this is a contribution. Okay. So now look at this. So here you have F1 minus 0 epsilon, but F1 minus 0 epsilon, I know that it fulfills this property, meaning that if I write in coordinate F11, F12, so the two components, when I use this one, what do I get? I get this, because I know that F11 minus 0 epsilon is real, but this means something, no? This means that if I don't know what the first component is odd and the second component is even. So F1 minus 0 epsilon, it is an odd x and an even function. And so this is odd x, even x. This is also odd x, even x. And then what do you get when you make the scalar product? So the first component is 0, so you have the scalar product between sine of d plus p0 times an even function 0, scalar product odd even x, scalar product sine of d applied to an even function is an odd function. Scalar product odd even is 0. But then you have a problem because we have this by 0. This might have an average. And so the scalar product with this with even x, there might be a contribution. Okay, so this function, this and this might have an average. So, and this is and if you compute it actually they have an average, so in principle it's correction. And so what you do, you change the basis. So solution is to work not with the basis f1 plus and 1 minus, so but you change basis and you change basis at the beginning, at the very beginning. So essentially achieve what we go for days, because you don't use this basis, you don't use the basis f1 plus and 1 minus to matrix, but you make a slight change of basis, and so solution do it on a different basis. So use a different basis, and in particular we use the basis G1 plus mu epsilon, which is F1 plus mu epsilon, G1 minus
mu epsilon, which is F1 minus mu epsilon, minus the scalar product of F1 minus mu epsilon, F0 minus mu epsilon, divided by the norm, F0 minus mu epsilon squared, and here you have G0 plus mu epsilon equal F0 plus mu epsilon plus F1 minus mu epsilon, F0 minus mu epsilon divided by the norm of F0 minus mu epsilon squared, and G0 minus mu epsilon, which instead is the same, F0 minus mu epsilon. So actually you do everything that I told you these 2 days on this basis. So in a sense I cheated on you, but not really. In the sense that this change of coordinates, this new basis, is again symplectic and reversible. So the new basis, G1 plus minus G0 plus minus, is again symplectic and reversible. Meaning that this two property holds, and it holds also the symplecticity property between these. And the form, the matrix representation, we prove it for any symplectic and reversible basis. So the property that I stated, the algebraic properties were true for any symplectic and reversible basis of the space in epsilon that you want to use. So the algebraic property holds also for this basis. So the cancellations that I told you in the first minutes holds also spaces exactly the same. They are algebraic and they hold for any reversible and symplectic basis, and this is symplectic and reversible. And moreover, now this element, when you evaluate at 0, at mu is equal to 0, u1 minus 0 epsilon, which is f1 minus 0 epsilon, minus what is this guy? Scalar product f1 minus 0 epsilon, f0 minus, what is f0 minus? F0 minus, if you remember, is 0, 1. Is 0, 1, meaning that from the vector f1 minus 0 epsilon, I'm removing the average of the second component. So this, and then this another equation. I'm removing the average of the second component, so this basis, so this element in the second component has 0 average. So this has the form, this must have the form odd, something odd, times a function even the second component, but with 0 average. Okay, so now in this basis, this is a function with 0 average. When I do this computation on this basis, is a function with 0 average, so this is an even 0, and so pi 0, even 0, it is 0. And so you get it is exactly 0. And this change of basis is just it's a higher order perturbation of f1 plus, f1 minus, f0 plus, f0 minus, meaning that you don't change the Taylor expansion. And that will be different. They are higher order perturbations of this type. You are not going to you are not going to change. Okay, so sorry, I forgot here. Here there is f1 minus. Equal to 0. Here there is sorry, I forgot there is f 0 minus 0 epsilon, because we want to remove the component second average. also here it should be F0 to make it symplectic. Should be
Because this gives you the projection where
yes.
you want to keep the direction, so you have to write instead.
Yes, exactly. I want to remove the average. So okay. And I think 0 minus because you want to remove the number. You want to remove it. Mu epsilon here. You have everything, and then when you evaluate here, you remove the average in the second component. And so it will have an average. Okay. So in the remaining time, let me explain the last. Okay, so now we've got this expansion, and now what I want to do is to tell you how to complete the proof. So the last step of the proof is to block diagonalize that matrix in such a way that you arrive at a block diagonal 2 times 2 matrix. Half an hour, I think I find seconds of the producer, the block organization. Okay, so now the goal is to look for a block decoupling. So block decoupling. So what I want to do is to look for a change of coordinate phi such that so look for a symplectic for phi symplectic, always symplectic and always reversibility preserving transformation such that phi minus 1 L mu epsilon phi is actually a 2 times 2 block. So it is something like G2 D nu 0 0 J2 G nu with nu more or less the same with nu having the same expansion as E and G nu has the same expansion as G and maybe there is no time because you know this matrix, you know the values of matrix and then you know the values of. So the spectrum is clear. So why should we expect? Why should we expect that it's possible to do? So when it's possible to put up the block diagonalization. So the intuition idea. So in principle, when you can do a block diagonalization of this type, so you can do a block diagonalization if the distance between the spectrum of this block of J2E, the spectrum, if the distance between the spectrum of this and the spectrum of this is much smaller than the coupling. Philosophically, the distance between the spectrum of the spectrum of J to J is much smaller than the coupling, so the size of the perturbation. Okay, so if you see this as a diagonal matrix plus a small perturbation, and you want to diagonalize it, philosophically, you want the distance between the spectrum of this and the spectrum of this is much smaller than the spectrum of this. So the spectrum of J2E, it has size roughly on mu, and this instead has the spectrum of this as sides around the square root of mu, and the perturbation is f, which I wrote it here, but you see there is an element of order epsilon to the cube. So this is something of order there's the size of f, so it is epsilon to the cube, mu epsilon. And so, well, good at this tell that you want this, that's well, you want a square root of mu much smaller than epsilon to the cube, but this is not good for us, no? Because this would connect, this would link mu and epsilon. Instead, we want them to be independent. We do not want to take mu small with epsilon, because this would allow us to have the complete description of the eigenvalue. So we want that mu and epsilon can move in small intervals, but independent of each other. Okay, instead, this is a constraint on we can move one is one is. Okay, so okay, so the first step of block decoupling is that so you see this element. So the dangerous one here is the epsilon to the cube, and this comes from this element. This is the only terms in which there is a terms of this type. Yeah, all the other terms have at least a mu or a mu squared, so they are fine. And the dangerous one is this. So the first thing that I want to do is to make a transformation which kill this element completely. So you put it at 0. So this is the first step of the coupling. First step. Remove F11. And this can be done by a quite explicit transformation. So I write it down, so there doesn't matter. So there is an explicit transformation, so there exists Y, an explicit transformation, which does the game. Actually, I can write it explicitly, so easy. Which is identity minus F11 divided by G11. So F11 is this element, and G11 is instead this element, which is 1 plus some correction, lower order correction, times the 2 times 2 matrix of the form 0 minus P Q 0, and P is a matrix 0 0 0 1, Q is equal 1 0 0 0. So the transformation is again symplectic, and reversible, reversibility preserving. And so if you make LU epsilon, you define this to be the conjugate. So if you conjugate your matrix by this, then you get another matrix of the form J4, B mu epsilon 1, in which B1 mu epsilon, it has the form, there is a new one, a new E, there is a new F, there is a new F1 star, there is a new G1. This matrix expands exactly in this way. So I will put here 1, except now that you have completely removed this element. And so now this has become 0. This is just computation. Take this matrix, conjugate L with with the matrix Y, and you discover that you have matrices of this form. So this is G1. The novelty is that now here we have exactly 0, and you have a 0. So exactly. Okay. Okay, the second step of decoupling, now we can start the perturbative schema. And now the second step is to make another change of coordinates to conjugate this matrix to a new one in which these two parts are more or less the same. But the route diagonal part have a smaller size, much smaller size. So in particular, here you see I have this is something of order mu epsilon, mu squared. I want to go to something which is mu squared, epsilon and mu to the cube. I want to reduce the size of this. So second step. Remove conjugate L mu epsilon 1 to a new matrix with the norm of F2 with the new out diagonal term much smaller than the term of F1. Okay. And what do I do? So I look for a matrix S, which is Hamiltonian and reversibility preserving, such that L mu epsilon 2 is equal to E. Okay, so now I conjugate with a matrix which has this form, exponential of S, in such a way that this is symplectic and reversible. Ah, sì, so my transformation must be reversible, non reversibility preserving. In such a way that no, reversibility preserving. So this is okay, L mu epsilon E to the minus S in such a way that this is the new matrix of the form J2 E2 is again Hamiltonian, so it has a little structure G2 F2 J2 F2 adjoint J2 in the new matrix G2 in which E2 and J2 as all still this same this expansion, and this has become of much smaller size. Of much smaller size, and in particular how we get a unit, or we get a unit. Okay, why do I choose so now here the point is how to find S. Now how to find a matrix S such that when you do this conjugation, you get some you're able to reduce the part of the outer diagonal there. Okay, and here you do so the method to use is it is the expansion. Which is this. So let me take or maybe you know. So you know so the matrix S will be in any case small in size. So this is transformation close to the identity. And do you know how this object expand? So this expand in this series. Okay, it has a perturbative expansion in this series, and now I'll tell you how to do it, but it's very easy, but it's a very flexible method. So define this minus PS L e to the minus PS. Define this. This is a function in T, so add a fictional parameter T. And then what do you have? So compute what is f prime of T. F prime of T, when you take the derivative, So this is E to the 3S, and then you have the commutator between SL, E to the minus 3S, and then when you take the second derivative, what you get? So you get a second commutator, ETS, S commutator, SL, E to the minus 3S. Okay, so the object that you want to compute, what is the object that you want to compute? What is? Well, this is f of 1. Taylor series. This is f of 0 plus f prime of 0 plus 1/2 f second of 0 plus integral between 0, 1, 1 minus tau square f 3 times t. And so what is this expansion? So f0 is so this is e to the s l e to the minus s. This is L. This is the commutator between S and L. This is 1/2 commutator between S, L, and you go on. Okay, so this is an expansion in commutators. Okay, so I have this matrix and I want to make an expansion in commutators, but separating the diagonal and the off-diagonal part. So I write L as a diagonal part plus an off-diagonal part. So the diagonal part is J to E, 0, 0, J to G, and the out-diagonal part is the perturbation, so it's 0, J to F, J to F star 0. And now let us make a commutator expansion. So what do we get? So we get E, S, E plus R, E to the minus S, what is? So first I do a commutator expansion D, and so I have D plus the commutator between S and D plus 1/2 the double commutator SSD plus the remainder, which comes from the integral formula, which is very small. And what about R? So then I have, well, I have R, which I put it here. Then I have the commutator between S and R plus higher order terms. And why do I write it in this way? So I write it in this way because I look for S. I look for S. Okay, so now you see why? Because I want to look for S in such a way that this is 0. So look for S, a matrix. So S is a 4 times 4 matrix, and I look for S always in this form J4 0 sigma star 0 in such a way that it is a Hamiltonian, and I want to look for S in such a way that this is equal to 0. And then if this is 0, so if S is if of small size, and this is 0, then the other correction, which comes from this term, which be of smaller size, because they will have the size of S. For example, this will have the size of S squared. So this will be, so for example, this, if S is small, this is a commutator between S and R is smaller than R. And so on, no? Also the remainder term and the new diagonal part, the new diagonal part that I generate will be the commutator, will be something which is formed by taking commutator S. S is small size, so I have reduced the size. Okay, so okay, so okay, so I want to solve the homological equation. Solve the homological equation. Commutated between x d plus r equal to 0. And then if you look s of that size and you compute what is this object, commutator s dr, so this amount to solve is equivalent to solve the matrix so this and then also look for and then look for sigma. Sigma is a 2 times 2 matrix. Look for sigma of the form J2 times a matrix X and the matrix S of the form 2 times 2 X11, I X12, I X1, X22. So all of these, and then this equation is equivalent to solve the equation of the form E1, so J2E. So J2E X minus S J2G equal minus J2F with the computation. And this is a Sylvester type equation. Okay, so this is an equation of the form of this Sylvester, Sylvester equation. The equations, so the other equations of the form AX minus XB equal to Y. And there is a general solution that there is a general method that you can solve this kind of equation provided you can solve this Sylvester equation provided the spectrum of A, the spectrum of B are separated. And this is the case, no? Because J2E, so the spectrum of J2E, something of order mu, the spectrum of J is something of order square root of mu, so they are separated. And so you can solve them. You can solve this equation, but actually, this is a 4 times 4 system. This is a 4 times 4 system, and you can solve it also directly. And we solve it directly because we want that X is analytical inside of NP. You can also solve it directly and find the matrix X this is. And this is what it is. So we solve it directly. And also, so this is a 4 times 4 system, you can write explicitly. So write it explicitly. So let me say this after. So star is equivalent of the form A and the vector X equal F. And so X is equivalent to 1F. And then we can also check that this is something of order with a something of order 1 over mu, and F is instead the size of the perturbation, so it is something of order mu epsilon times mu squared. Okay, so F is a certain order. So these are the component of the matrix in the column vector. And so you see that although this is a singular matrix, this remainder, so this fact is F is already sufficiently smaller, such a way that this 1 over mu will cancel out the order is, and so together this will be something of order epsilon. Okay, so this means that this matrix X is of order epsilon, and so this S also is of order epsilon, so it's of both sides. So this turns out that S is of order epsilon. Okay, but this in principle it might be a problem. This might be a problem because so check on this correction. So here we have okay, SD is equal to minus R, no? So this is minus R, and so this is commutator S minus R. So the minus goes here, this cancel out, this rule, this commutation, this becomes plus 1 over alpha. Now, what is this? So this is an object of size. What is this object? So this object is, so S is out diagonal. R is out diagonal. This commutator is a diagonal. So in this diagonal correction, the matrix is diagonal matrix. And what is the size of this correction? The size of this correction, it is, so S is of order epsilon. R is the out diagonal term, so it's this. So you see there is a term of mu epsilon. So this is epsilon square mu. This might be bad in principle because the term of the, so if there is really the terms for epsilon square mu, so this is a correction to the diagonal part. So if there is a correction for the mu epsilon squared here, so I spent quite effort to try to remove, so to prove that there are no terms on this side, mu epsilon something entering here. So if this had a correction to this element, this will be problematic. But fortunately, so everything is very explicit, so you can compute exactly the size of every element, and you realize that okay, it's true, there are corrections of order epsilon square mu, but never to this element. So there will be correction entering here, but it's not a problem because here we are for the epsilon square mu. There will be perturbation here. There will be correction epsilon square mu here, but it's not a problem because you already propagate the mu, which is much the large size. And instead, exploiting bringing the computation directly to discover that there are member correction of the type and and so there's some by direct computation. And this is also why we make this first step explicit. So in order to prove that this new correction, whoever the exact correction of the diagonal part, and to prove that this new matrix has exactly a structure. So now two, and instead of using two, and instead now step 2, you can also prove that the new out diagonal correction are much smaller, and in particular you always get the mean. So I reduce the size. Okay, and then to conclude, we do another step of this plot decoupling. and you remove complete. So now they are diagonal term sufficiently small in order be removed completely with less effort. And so the final step is do the final block diagonalization. We do the third step is a complete diagonalization, proceeding more or less in the same way. So third step, complete block diagonalization. Now the remainder. So now the remainder is sufficiently small size. And so again, you look for a second matrix, look for a new matrix, the second matrix has 2, such that when you make L mu epsilon 3 defined as E to the so actually you can also put on the diagram because smaller into the mu S2 L mu epsilon 2 into the minus mu S2, then you remove completely the diagonal term and you are left with a matrix which is J2 to 3 0 0 J2 G3 and you will at this time when the perturbation is very small and so it has not corrected much. So it has corrected it has corrected these elements, but only the perturbative way. So the asymptotic expansion stays the same. G3 is for the J2, and so at the end you have all these, and you have 2 times the matrix. And now you can compute the effects. And you discover that they have measure effects. Stability, and that's it.